Hello everyone. In the previous lesson, you learned about the Lewis theory, which is one of the simplest bonding theories in molecules. The Lewis theory is also known as the Lewis model, and this model basically shows you how atoms are bonded together within a given molecule. And bonding involves the valence electrons, which are the outermost electrons in a given atom. You also learned about the three different types of chemical bonds: metallic bond, ionic bond, and covalent bond. Covalent bond is the sharing of electrons between atoms, and this is the bond that is utilized in molecular compounds, also known as molecules. Very few molecules, such as the homonuclear diatomics, have bonding electrons that are shared equally by the atoms. But in most molecules, the electrons are shared unequally due to the difference in the atom's electronegativity. The more electronegative atoms tend to be more electron dense than the less electronegative atoms, which results in the separation of charge known as dipole. And this makes the bond between them to be polar. And finally, you'll learn about the strength and the length of the different covalent bonds. Triple bonds contain the most energy and the most difficult to break, whereas the single bonds contain the least energy and the easiest to break. Single bonds are the longest and triple bonds are the shortest. In this chapter, you will learn about Vesper Theory, the polarity of molecules, geometry of simple molecules, and the valence bond theory. The Vesper Theory, which stands for valence shell electron pair repulsion, introduces the concept of electron groups that repel each other, which results in the formation of a three-dimensional molecular structure with specific bond angles. These electron groups can be any of the following. A lone pair of electrons counts as one electron group. A single bond counts as one electron group. A double bond also counts as one, and so does a triple bond. And you don't have to worry about free radicals here, but free radicals, by definition, are a single unpaired electron. So by knowing the total number of electron groups of a central atom within a given molecule allows you to determine the geometry of that molecule. So how do we count the total number of electron groups of a central atom within a given molecule? Well, let's take a look at a few examples here. Let's say that we have this molecule shown here, and this is the geometry of the molecule, the structure of the molecule. How do we count the total number of electron groups? Well, first you have to determine which one the central atom is. This atom in red is going to be the central atom. And the central atom has either a single bond or a double bond with the terminal atom in black. And so that counts as one electron group. And then this other bond right here, again, this could be a single bond, a double bond, or a triple bond. And this also counts as one electron group. So the total number of electron groups of the central atom would be 2. So in this example, we have a total of 2 electron groups. And with any molecule with 2 electron groups, the bond angle between the terminal atoms, the bond angle between the 2 terminal atoms will be 180 degrees. Okay, so let's take a look at another example here. So let's say we have this second molecule shown here, and this is the structure and geometry of the molecule. You have 3 terminal atoms, and you have the central atom again in red. How many electron groups does the central atom have? Well, again, you could have a double bond or a triple bond here, or it could be all single bonds. So in that case, this central atom has a total of 1, 2, 3 electron groups, regardless whether it's a lone pair, a single bond, a double bond, or a triple bond. So we have a total of 3 electron groups, and the bond angle between the terminal atoms would be 120 degrees. And here's another example. Here we have the central atom in red, and this time we have 4 terminal atoms. And again, these bonds between them could be a single bond, double bond, or a triple bond, or it could be just a lone pair of electrons. So in this case, the central atom in red has a total of 4 electron groups: 1, 2, 3, and 4. And so the bond angle between the terminal atoms is 109.5 degrees. So the main goal in this first half of the lesson is to learn how to assign electron geometry and molecular geometry. And these two things are different, but they are related. So what's the difference between electron geometry and molecular geometry? In electron geometry, you're focused on the number of electron groups in a central atom within a given molecule. Whereas in molecular geometry, you're taking into account the difference between lone pairs and bonding pairs. So you can think of electron geometry as the main type, the main geometry, whereas the molecular geometry is the subtype. So let's take a look at the different types of electron geometry here. The first one is linear. A linear electron geometry, or a molecule with a linear electron geometry, has two electron groups. So if this atom in red is the central atom has two electron groups, and automatically that molecule has a linear electron geometry. The second type here is called trigonal planar. Okay, and trigonal planar has three electron groups. So again, if this is the central atom in red, we have 1, 2, 3 electron groups. And that molecule automatically has a trigonal planar electron geometry just because of the fact that it has 3 electron groups. The third type is called tetrahedral. And a tetrahedral molecule has 4 electron groups. Okay, so again, the central atom here in red has 4 electron groups, which makes this molecule a tetrahedral molecule. The fourth type is called trigonal bipyramidal, and the central atom has a total of 5 electron groups. And the fifth one is called octahedral, because it makes an octahedron shape, which means that the molecule has a total of 6 electron groups. So this central atom has 1, 2, 3, 4, 5, and 6 electron groups. So these are all the 5 main types of electron geometry, and you need to remember all of these. So now let's take a look at molecular geometry. So earlier I mentioned that electron geometry can be thought of as the main type and the molecular geometry as the subtype. And so if we have a linear electron or a molecule with a linear electron geometry, the molecular geometry is also linear, and that's the only subtype. What about a molecule with a trigonal planar electron geometry? The molecular geometry would either be a trigonal planar or bent. So that means you have 2 subtypes. So trigonal planar has 2 subtypes, either trigonal planar or bent. What about tetrahedral? For tetrahedral, you can have 3 different subtypes, 3 different molecular geometry. Right? It can either be tetrahedral as well. It could be trigonal pyramidal or bent. And the fourth one here is trigonal bipyramidal. So a molecule with a trigonal bipyramidal electron geometry will have 4 different subtypes or 4 different possible molecular geometry. So the first type or subtype is trigonal bipyramidal, which is similar to the electron geometry. You can have a seesaw molecular geometry, T-shaped or linear molecular geometry. And finally, if you have a molecule with octahedral electron geometry, you can have 3 different subtypes or 3 different molecular geometry. The first one is octahedral. So an octahedral electron geometry can also have an octahedral molecular geometry, square pyramidal molecular geometry, and square planar. So let's focus more on the electron geometry. How do we determine the electron geometry of a simple molecule? So I mentioned earlier that it's important to be able to determine the number of electron groups of the central atom for a given molecule. So if you know the total number of electron groups of a central atom in a molecule, then you'll be able to determine the electron geometry of that molecule. So for linear, if the central atom has 2 electron groups, then you know that it's going to be a linear molecule. If you have a molecule with 3 electron groups, then you know automatically that it's going to be a trigonal planar. A molecule with 4 electron groups will automatically be a tetrahedral molecule, or a molecule with a tetrahedral electron geometry. And a molecule with 5 electron groups would automatically be a molecule with trigonal bipyramidal electron geometry. And with 6 electron groups, it would be octahedral. So let's take a look at a few examples here. So let's say we have BF3, which is boron trifluoride. When you draw the Lewis dot structure, you can see that the boron, the central atom, has 3 electron groups total. And so its electron geometry would be trigonal planar. Carbon dioxide, when you draw the Lewis dot structure for carbon dioxide, you can see that carbon is the central atom, and carbon has 2 electron groups, right? A double bond counts as a single electron group, and we know that carbon has 2 double bonds, and so it would have 2 electron groups, and this would be a linear molecule. And the third example here is ammonia, which has the chemical formula NH3. And as you can see, the nitrogen is the central atom, and it's got 1 lone pair and 3 single bonds. So each single bond counts as 1 electron group. And so we have 1, 2, 3, 4 electron groups. So in that case, ammonia has a tetrahedral electron geometry. And the last example here is selenium hexafluoride. So when you draw the Lewis dot structure, it looks something like this, where selenium is the central atom, and it has a total of 6 electron groups. 1, 2, 3, 4, 5, 6. And because it has 6 electron groups, selenium hexafluoride has octahedral electron geometry. So let's take a look at a few more examples here. So all these 3 molecules, carbon dioxide, carbon disulfide, and beryllium chloride, will have a linear electron geometry, which means that the central atom, carbon and beryllium, will have 2 electron groups. Boron trichloride and the nitrate ion will have 3 electron groups on the central atom, which means that it will have a trigonal planar electron geometry. Molecules such as methane, CH4, ammonium ion, and the sulfate ion will have a tetrahedral electron geometry, which means they have 4 electron groups. Both PF5 and sulfur tetrafluoride will have 5 electron groups total, which means that they both have a trigonal bipyramidal electron geometry. So how do you think that SF4 has a trigonal bipyramidal electron geometry when it only has 4 atoms bonded to it? Well, that must mean that the sulfur has a lone pair of electrons. So that lone pair counts as 1 electron group. And so you have 4 fluorines, that's 4 single bonds, plus the lone pair of electrons. So a total of 5 electron groups, which means that it's going to have a trigonal bipyramidal electron geometry. And the last one here, we have SF6, sulfur hexafluoride, xenon tetrafluoride, and bromine pentafluoride. So each of these molecules will have 6 electron groups, which means that they will have an octahedral electron geometry. So it's easy to see how sulfur hexafluoride would have 6 electron groups because it has 6 fluorine atoms. For xenon pentafluoride or xenon tetrafluoride, it has 4 fluorine atoms single bonded to the xenon, which means that the xenon must have 2 lone pairs of electrons, which makes it a total of 6 electron groups. Same thing for bromine pentafluoride. The bromine atom, which is a central atom, must have a lone pair of electrons. So now let's switch gears here and focus more on molecular geometry. And I mentioned earlier that molecular geometry is basically a subtype that takes into account the difference between lone pairs and bonding pairs. So here's a list of the different types of molecular geometry based on the molecule's electron geometry. If the electron geometry was linear, the molecular geometry would also be linear. So that means there's a total of 2 electron groups. If the electron geometry was trigonal planar, then there are 2 different types of molecular geometry, either trigonal planar or bent. And so that means that both of these molecular geometries have 3 electron groups total. And the third type here, if the electron geometry was tetrahedral, then the molecular geometry could either be tetrahedral, trigonal pyramidal, or bent. And the number of electron groups here would be 4. And the fourth type here is if you have a trigonal bipyramidal electron geometry, then the molecular geometry could either be trigonal bipyramidal, seesaw, T-shaped, or linear. And the number of electron groups here would be 5. And the last one, if you have an octahedral electron geometry, then you can have 3 possible molecular geometry, either octahedral, square pyramidal, or square planar. And they all have 6 electron groups. So if you have a molecule with an electron geometry that is linear, then the molecular geometry will automatically be linear as well, okay, with 2 electron groups. So what's the difference between trigonal planar and bent? So what's the difference between these 2 types of molecular geometry for a molecule with 3 electron groups? Let's take a look. So let's say that we have a molecule here with a central atom and 3 terminal atoms. So because you have 3 terminal atoms, then the electron groups, all 3 electron groups here are bonding groups or bonding pairs, right? And so because we have 3 bonding pairs or 3 electron groups, the electron geometry will be trigonal planar. And because you have all 3 bonding pairs or bonding groups, the molecular geometry will also be trigonal planar with 120-degree bond angles. Now, what if we replace one of the terminal atoms with a lone pair? So now we have 2 different types of electron groups. We have a lone pair and bonding pairs, right? So we have 1 lone pair and 2 bonding pairs. So in that case, this molecule would have a trigonal planar electron geometry, but the molecular geometry is going to be bent just because of the fact that it has 1 lone pair of electrons. And so the bond angle between the 2 terminal atoms would be less than 120 degrees. Okay, so for this one example here, the electron geometry will be trigonal planar, but the molecular geometry is going to be bent. For a molecule with 4 electron groups, you can have 3 possible molecular geometries. You can have either tetrahedral, trigonal pyramidal, or bent. Now, this will also depend on the number of lone pairs versus the number of bonding pairs. So let's say that we have a tetrahedral molecular geometry. So what that means is that you have 4 bonding pairs of electrons. Okay, 4 electron groups, and all those electron groups are bonding pairs of electrons. And so the bond angle between the terminal atoms will be 109.5 degrees. And if you replace one of the terminal atoms with a lone pair, then this is going to be a trigonal pyramidal molecular geometry. Okay, and the bond angle between the terminal atoms will be less than 109.5 degrees. And lastly, if you were to replace one more terminal atom with a lone pair, then what you have is a bent molecular geometry, and it looks something like this. So you have 2 lone pairs of electrons and 2 bonding pairs. And so the bond angle between the 2 terminal atoms will still be less than 109.5 degrees. For molecules with 5 electron groups, you can have 4 different molecular geometries. You Could either be trigonal bipyramidal, seesaw, T-shaped, or linear. So what's the difference? Again, the difference would be in the number of lone pairs of electrons, right, versus the number of bonding pairs. So if you have all bonding pairs of electrons, meaning you have a total of 5 terminal atoms, then the molecular shape or molecular geometry is the same as the electron geometry. In this case, trigonal bipyramidal. And so the bond angles will be different. You can have a 180-degree bond angle. You can have a 120-degree bond angle and a 90-degree bond angle. Now, if you replace one of these terminal atoms with a lone pair, according to Vesper theory, you can minimize the repulsion of the electrons by making one of the equatorial atoms as the lone pair. Okay, so you have less repulsion if the lone pair was in the equatorial position instead of axial. So axial means top or bottom. Okay, and so this is called seesaw because it looks like seesaw when you rotate this 90-degree clockwise. It looks like a seesaw. Okay, so the molecular geometry is seesaw if you have one lone pair. If you have 2 lone pairs of electrons, well, let's talk about the bond angles. So the bond angle between these 2 atoms, terminal atoms here, would still be 180 degrees. And then the bond angle between these 2 will be less than 120 degrees. All right, replacing one of the equatorial terminal atoms with a lone pair would create a T-shaped molecular geometry. All right, so it's T-shaped because of the fact that it looks like the letter T. Okay, so it makes a T shape here. So you can rotate this again 90-degree clockwise, and what you have is a T-shaped molecule. And the bond angle between them, you have 180 degrees between the 2 axial atoms, and then 90 degree between these 2 atoms here. All right, and if we replace another terminal atom with a lone pair, we would replace this with a lone pair, the last equatorial terminal atom. So in that case, what you have is a linear molecular shape. So you have 2 atoms that are in the axial position and all the lone pairs in the equatorial position. So again, the bond angle between the 2 terminal atoms would be 180 degrees. And the last one here is for a molecule with 6 electron groups. So if you have a molecule with 6 electron groups, the electron geometry would be octahedral. And an octahedral electron geometry has 3 possible molecular geometries. It's either be octahedral, square pyramidal, or square planar. So what's the difference between these 3 molecular geometry? So if you have all terminal atoms bonded to the central atom, then you have an octahedral molecular geometry because you have all bonding pairs. All the 6 electron groups are bonding pairs. And the angles between them would be 180 degrees here, 90 degree here, and that's pretty much it. 2 different bond angles. What about for a square pyramidal? If you have one lone pair, it could be any of these atoms. So you can replace any of these terminal atoms with a lone pair. So let's say that we remove one of the lone pairs here at the bottom. Now this would be a square pyramidal. So it basically has a square base and it basically looks like a pyramid. So they call this a square pyramidal. And the last type here is called square planar. And the bond angle, by the way, is 90 degrees between these 2 atoms and then 180 degrees between 2 opposite terminal atoms. And the last type of molecular geometry here is square planar, which means that it basically a square-shaped molecule that's sitting on a plane, right? So if you have a two-dimensional plane, you have a square. So if we were to replace one of the other terminal atoms here, it would be the one that's opposite the lone pair. Okay, so in that case, it would be this atom that's in the axial position. Okay, so if you replace that, you're minimizing the repulsion between the electron groups. And so in that case, what we have here is a square planar molecular geometry with 90-degree bond angle. 90-degree bond angle and 180-degree bond angle as well. Okay, so let's take a look at this one problem here. Determine both the electron geometry and molecular geometry for the following molecules or ions and sketch the structure with bond angles. Alright, so the first one we have here is a phosphate ion, PO4 with a -3 charge. So when you draw the Lewis dot structure for a phosphate ion, it looks something like this. We have the phosphorus as the central atom, and then the oxygen atoms as your terminal atoms. And as you can see, the phosphorus atom has a total of 4 electron groups. And so because it has 4 electron groups, the electron geometry is going to be tetrahedral. And a tetrahedral molecule has bond angles that are 109.5 degrees. And so because all of the terminal atoms here, or all of the electron groups are bonding pairs, then the molecular geometry will also be tetrahedral. Okay, so electron geometry and molecular geometry are both tetrahedral for the phosphate ion. So for the second example here, we have chlorine trifluoride. Okay, and so when you draw the Lewis dot structure for chlorine trifluoride, it looks something like this, where chlorine is your central atom and you have 3 fluorine that are terminal atoms, and the 2 lone pairs would be in the equatorial position. So if it helps you visualize this a little bit better, you can draw an electron cloud around the electrons, the lone pair of electrons. Okay, so because you have 2 lone pairs, or a total of 1, 2, 3, 4, 5 electron groups, the electron geometry is going to be trigonal bipyramidal. Okay, and the molecular geometry would then be T-shaped, right? Because this looks like a T formation here. Okay, and so the bond angles between them, between the fluorine atoms, would be 90 degree here, and then 180 degree between the 2 opposite fluorines. And the last one here is bromine pentafluoride. So when you draw the Lewis dot structure, it looks something like this, where bromine is your central atom, and bromine has a total of 6 electron groups, 1, 2, 3, 4, 5, 6. And so this is an octahedral molecule. So the electron geometry is octahedral, and because you have 1 lone pair of electrons, the molecular geometry is going to be square pyramidal, okay? Because it looks like a pyramid with a square base. So this is a octahedral electron geometry with square pyramidal as the molecular geometry. And the bond angles between the fluorine atoms, for example, these 2 fluorine atoms right here will be 90 degree angle, and the bond angle between 2 opposite fluorine atoms will be 180 degrees.